Hello and welcome to another exciting calculus video. In this one, we're going to do the section 2-5 from the textbook. It's called Implicit Differentiation. And let me introduce it this way. Here is a function, y equals x cubed plus 2x squared plus 1. Now, when we say we derive with respect to a variable. So here, we're going to derive the y function, dy, with respect to the x variable. So it's dy dx. And this is the deriving we've been doing, since the start of this chapter. We're going to derive this as usual. So bring down the exponent. That would be 3x to the second power. And then we're going to have a 4x to the first power, and the 1's going to derive away. So there's our derivative. But what would be the case if we were not deriving with respect to x? Let's say we were going to derive y, but with respect to t. Now that's a different variable that doesn't appear here anywhere, but it's still going to be able to be derived. Again, we're deriving x's, but now with respect to a different variable. So this is kind of just an extension of the chain rule. Let's imagine this x is our inner function. So if we're going to derive, of course, we're going to bring the 3 down front. The x is going to stay the same, and the variable drops 1. But now since we're deriving with respect to t, and this is a different variable, remember the chain rule, we need the inner function's derivative. So we're going to add to this a dx dt. And let's derive the next term, 2x squared. Well, that will bring down the 2. We'll hit that 2 and become a 4, x to the first. But again, x is the inner function. And since we're deriving with respect to t, we're going to chain rule a times dx dt. Now, just for the sake of argument, too, let me go down here and let's say after this 2x squared, what if we had a 3t to the third? Well, now since we're deriving with respect to t and the variable is a t, we would just derive this term as usual. That would be 9t to the second. No little extra pieces created because we were deriving with respect to that same variable. Okay, well, buckle up, buckaroos. Let's jump on in here. 2-5, we're going to learn to distinguish between functions written in implicit and explicit form. We will use implicit differentiation to find the derivative of a function. And actually, we can use this to find derivatives of non-functions, that would fail the vertical line test. And we'll find derivatives of functions using the logarithmic differentiation style. Okay. Up to this point in the text, most functions have been expressed in explicit form. For example, this equation, y equals 3x squared minus 5, the variable y is explicitly written as a function of x. Some functions, however, are only implied by the equation. For instance, if we look at this x times y equals 1, we could get the y by itself by dividing by x. So we get y equals 1 over x. So this is an implicit equation. Implicit x times y equals 1 is the same thing as y equals 1 over x. This is the explicit form. This is the implicit form. To find the derivative, dy dx, for this equation, we write y explicitly as a function of x, then derive. So here's our implicit form. Divide both sides by x, we rewrite it with the negative exponent, and then we derive. Dy dx equals negative x to the negative 2, and we rewrite it with our good math manners so we don't have negative exponents, and there's our derivative. This strategy works whenever you can solve the function explicitly. You cannot, however, use this procedure when you are unable to solve for y as a function of x. For example, how would you find dy dx for this equation? If we try to get the x by itself, or the y by itself, we're going to run into trouble. If we move the x squared over, we could sort of block these off and factor out a y, but then there's still going to be a y squared inside. It's going to be difficult or impossible to get the y variable by itself. So to derive this, we would use implicit differentiation. To understand how to find this derivative implicitly, we must realize that differentiation is taking place with respect to a variable, usually x. This means when you differentiate terms involving just x's, we can differentiate as usual. However, when you differentiate terms involving y, we must apply the chain rule because we're assuming that y is defined implicitly as a differentiable function of x. So here in example 1, some baby steps. Part A, we are deriving with respect to x, d dx. We are deriving x to the third. Notice the variables agree. So we're just going to derive as usual, bring down the exponent, keep our base, lower the exponent by 1. 3x squared is our derivative. In part B, now we're deriving with respect to x, but our variable is y, so the variables disagree. So we are going to start deriving this like you would expect. Y to the third is going to derive to a 3y to the second. That's a terrible 2. There we go. But remember, technically, this y is our inside function. So for the chain rule, we need to derive that inside function, and we're deriving with respect to x, so we're going to tack on a dy dx component. And there's our implicit derivative. Let's try a few more. Okay, letter C. We are deriving with respect to x. Our first term is an x, that'll be no problem. And our second term has a y, so we're going to do this implicit. All right, so the first one, let's derive x with respect to x, so that's just going to be a 1. And then we have a plus. Okay, we're going to derive 3y with respect to x. So first we derive and get the derivative 3 like we would expect, and then the y would disappear. But remember, y is an inside function, so we chain rule a dy dx on there. So there's our derivative. And this also works even if we're going to do a product rule. So I'm going to just write this up here. Our function is x times y squared. So when we derive with respect to x, the derivative of x with respect to x is a 1. When we derive the y squared, we're going to get a 2y, and then since we have a variable mismatch, we will tack on a dy dx. So there's our setup. Let's apply the product rule. So dy dx, just d dx, the derivative with respect to x, is the first thing times the derivative of the second plus the second thing times the derivative of the first. And there's one little thing I do to clean this up. Usually I put my dy dx as last, so I would just rearrange this first term into a 2xy dy dx plus a y squared. So there's our product rule derivative. All right. Guidelines for using this differentiation. 1. Differentiate both sides of the equation with respect to x. Collect all terms involving the dy dx differential on one side of the equation. Move everything else to the other side. Factor out the dy dx and then solve and get the dy dx all by itself. They seem pretty simple, but sometimes you run into some tricky algebra, but we'll get through it. In example 2, note that implicit differentiation can produce an expression for dy dx. We're going to find a derivative, and our derivative contains both x's and y's. So if it comes to a point where we're going to plug in a point to find a slope, usually we've got a point like, let's just say 2, 4. Usually we find the derivative f prime and put the x value in. When we find a derivative implicitly, there might be spots to put the x's in, and there might be other spots to put the y's in. And we'll see that pop up in a future example. So here we go. This is example 2. Find the derivative dy dx of this function. Notice we got y cubed, y squared, a y, and an x squared. Let me see. Yeah, and here's what the graph is going to look like. Notice this is going to fail the vertical line test. So it's not really a function. If we put in a positive 1, we can either get a positive 1 out or a negative 3 down here. So the question is, if we were to find a derivative, we want to find a slope, we want a tangent line. We'd have one tangent line at 1, comma 1, a different tangent line at 1, comma negative 3. So of course our derivatives will also have y values, so we make sure we're getting the right slope at the right point. Okay, so we got a function here. It's equal to negative 4. Step 1 is derive both sides with respect to x. So let's see, our first term is y to the third. That's going to derive to a 3y squared, and I'm going to switch ink colors here so my dy dx's stand out. So there's our first term. Up next is y squared. That's going to derive to a 2y, and since the variables don't match, dy dx. Third term, minus 5y. That's going to derive to a minus 5. And then we will also have, via the chain rule, a dy dx. Okay. Our last one here is minus x squared. We are deriving with respect to x. So when we derive this, it's just a negative 2x. And then we've got our equal sign. On the other side is a negative 4, and constants derive to nothing. So there's our first step, differentiate both sides with respect to x. Now we're going to collect all dy dx's on one side, move everything else to the other side. And that's easy here. Just to save myself from rewriting all of this, I'm just going to move the 2x over where it's going to become a plus 2x. So now this is equal to a positive 2x. So there's step 2. Step 3, factor out the dy dx. So if I imagine a set of brackets around here on the left side, we are going to factor out dy dx. And then inside the brackets, we will have a 3y squared plus a 2y minus a 5, and that's equal to 2x. Last step is to get the dy dx by itself. So we're going to divide both sides by the quantity in the brackets. So our derivative, dy dx, is 2x in the numerator, denominator, 3y squared, plus 2y minus 5. Okay, so we found our derivative. Now I'm kind of disappointed, the problem stops right there. We found a derivative. I feel like finding a slope. Oh, I guess they got some of these here underneath the graph. I can't remember if I put this graph in your notes. But here, the point 2, comma 0, oops. So 2, comma 0 is this point right here. Notice 2 would also give you an output up here and down here. That's why we fail the vertical line test. But to specifically find the slope at 2, comma 0, we're going to turn all the x's into 2's and all the y's into 0. So that numerator x becomes a 2, and then our y values downstairs become a 0. So the first term zeroes out, second term zeroes out, third term is a negative 5. So our slope there is negative 4/5. And then they do that with a couple other points. At 1, comma negative 3, plug in x is 1, y is negative 3, you get out a 1/8. At 1, 1, you would get a 0 denominator, and that makes the function undefined, undefined slope. So again, our derivatives can now contain both x's and y's to find slopes at those different points. Oops, I see a little technology box down here. With most graphing utilities, it's easy to graph an equation that explicitly represents y as a function of x. Graphing other equations, however, can require some ingenuity. For example, to graph the equation given in example 2, we would use a graphing utility set to parametric mode. To graph the parametric representation, well, we're not going to worry about that. We don't get to that in Calc AB. All right. We are going to do something neat. I have an expression where we're going to find the derivatives for circles, both implicitly and explicitly. That's a fun little exercise. So it's meaningless to solve for dy dx in an equation that has no solution points. For example, x squared plus y squared equals negative 4 has no solution points. Because if you square something, it's positive, and if you add to something else squared, that's also going to be positive. Two positives can never add up to a negative. So that has no solution points. We could not derive it. If, however, a segment of the graph can be represented by a differentiable function, then dy dx will have meaning as the slope at each point on that segment. Recall that a function is not differentiable at A, points with vertical tangent lines, and B, points at which the function is not continuous. So here, example 3, it says, if possible, represent y as a differentiable function of x. Let's see if we can do that here. So what we want to do is just get the y value by itself. So if we start with x squared plus y squared equals 0, we would first subtract x squared, negative x squared, and then we would take the square root of both sides. So we would get y equals plus and minus the square root of some negative number. Notice that negative is not going to get squared away when we square x because it's negative quantity x squared. So here we're going to have no differentiable points. And if you think about it too, x squared plus y squared equals 0. The only thing that's true for is when x equals 0 and y equals 0. You know, this is, if you remember your functions from pre-calc, x squared plus y squared equals r squared is a circle. So this is a circle of radius 0. Graphically, this is just a dot at the origin, and we cannot take a derivative of just a point. You know, we're finding tangent lines for any dot. I could draw infinitely many tangent lines going through it. So that first one just makes no sense. It's non-differentiable. It's just a point. And I think, yeah, I got a graph here. So there it is. Yeah, x squared plus y squared equals 0. That's just a point. We cannot take a derivative. Let's try letter B. Now we got a 1 over there. Okay, so the first thing we want to get y squared by itself. That means we'll keep the 1 on the right and we will subtract the x squared. Now we can take the square root of both sides. So we get y equals plus and minus the square root of 1 minus x squared. Okay, so what does this mean? You know, we've got this plus and minus. So for every one x input, we'll have a positive and a negative output. Well, again, x squared plus y squared equals r squared is a circle. So what this is a circle of radius 1, centered at the origin. So here's our circle. The plus and minus, I'm going to make the plus positive in blue. So we have a positive radical 1 minus x squared. That is the top half of this circle. And I'll switch to green for the negative radical 1 minus x squared. That would be the bottom half of the circle. So if you want to find the derivative at a point on a circle, you could figure out, okay, it's in the top or bottom part. You could use the appropriate equation here, derive that, and then get your derivative. Or you could do it implicitly, and that's what we're going to do in an upcoming classroom activity. Okay. Ooh, and I guess the book has a graph. They're probably a little better than mine. There it is. Top half of the circle is the positive radical, bottom half is the negative radical. Finally here, now the x is no longer squared. This is not a circle. Again, we'll get the y squared alone by subtracting the x, and then we're going to take the square root. So again, we're going to have a positive radical 1 minus x, as well as a negative radical 1 minus x. So what this is a parabola opening sideways. Here's the graph. So the top half, or the positive radical, I'll hit here in blue. That's the stuff that's above the x-axis. And then we have a negative half of our parabola down here in red. Again, we could figure out, like let's say we've got a point up here, we would derive and plug into the top piece. If we had a point on the bottom half of the parabola, we would plug that point into the derivative of this function. Or we could just derive implicitly. Okay, what's up next? Ooh, here we go. And is this the one? Oh, no. Okay, that's coming up. Example 4. Find the slope of a graph implicitly. Determine the slope of the tangent line of the graph of this, x squared plus 4y squared equals 4, at this point, root 2, comma, negative 1 over root 2. Okay. Well, let's derive implicitly. I'm just going to recopy the function here, x squared plus 4y squared. That's a terrible squared. That's a little better, equals 4. So let's derive with respect to x. First term variables match, so that's a nice easy 2x. And then we're going to have here, it's going to be an 8y to the first, but we had a variable mismatch. So we create a dy dx, that little extra piece, by the chain rule, and that's equal to the derivative of 4 is 0. I see it every year. The number one mistake on these, for some reason, students, when they got this 4 on the other side of equals, they'll just bring it along for the ride and not derive it. Very common mistake. All right, steps 2 and 3, we want to get dy dx by itself. So we are going to, here's my equals, we're going to subtract 2x. So that gets this term by itself, and then we're going to divide both sides by 8y. So there's our derivative. The derivative of y with respect to x is negative 2x over 8y. Our derivative has both x's and y's in it, but that's okay. We've got this point to plug in. So our numerator, negative 2, gets multiplied by, I won't even need the parenthesis, the numerator gets multiplied by a root of 2. And then down in the denominator, we have an 8, and then our y value is negative 1 over the root of 2. Okay, well, we've got a fraction here. We're going to bring this up and flip it. And let's see. I guess we can just leave the 8 down here. We're going to bring that up and flip it. I'm going to come down here. We've got our negative 2 root 2. And I'm going to put that, well, I'll just leave the 8 down here. We can do it this way. When we bring it out and flip it, now it is a negative root 2 over 1. And I could multiply that both distinctly in the numerator. But since it's flipped, we can just sort of multiply straight across. Now that is a negative there that we're multiplying by. So let me move that out a little bit more. Okay. Now, if we multiply straight across, dy dx equals, we've got a negative. Well, that's right. We've got a negative times a negative, so that will make our derivative positive. And in the numerator, we've got this root 2 times this root 2. That's equal to 2 times 2 more is a 4. And then our denominator is 8 times 1. That's just 8. And then 4 over 8 is just 1/2. There's our slope that's occurring at the point. And let me bring out the graph, see if that makes sense. It's a positive 1/2 slope. So here's our graph. The point we were looking at, I just covered it up, root 2 comma negative 1 over root 2. So that puts us down here. We're in the bottom half of this oval. And then if we drew a tangent line, it is positively sloped. Okay, it looks like we got it. Good job. And I want to point out something in here. It does say determine the slope of the tangent line. When we derived, we could have plugged the point in right away into the raw derivative. If the direction said find dy dx, we had to get dy dx by itself. Now I point that out because of this problem. Example 5 is extremely algebra intensive. I have down here, I'll show you the algebra at the end, but I like you to work smarter, not harder. And it says here, determine the slope of the graph at a point. So what we can do, derive this implicitly and then plug in that point right away. A lot of times, the hardest part of these problems is the algebraic simplification. So if we can plug into the raw derivative, by all means, it makes life much easier. So here's our function, 3, quantity x squared plus y squared quantity squared. When I look at the left side there, that is going to be a chain rule. And then our inner function has x's and y's. There will be some implicit in there. And then on the other side of equals, we have a 100 times xy. And I'm going to do it like this. I'm going to put my xy in its own set of parentheses because obviously over here we're going to do a product rule. You could attach the 100 and the x together and make that one term and the y the second term. I'm going to derive the x and y as a product rule separately and then distribute the 100. So that's just my personal preference. Okay, let's get to deriving. Over here on the left, we're going to start by bringing the exponent down, hitting that 3. So that becomes a 6, and we still have x squared plus y squared as a quantity, but that has now been reduced to the first power. And then for the chain rule, we're going to multiply this by, implicitly, the derivative of the inside function. So the first term, x squared, derives to a 2x plus, and then we have our y squared, that's going to derive to a 2y, and then chain rule is going to give us a little extra dy dx piece. So there's the left side, and what I'm going to do to save room is sort of just scrunch this up a little bit. There we go. Now that's equal to, on the other side, we've got the 100. That's a constant multiple we'll save for the end. But we'll put our product rule derivative in here. The derivative of x, that's just a 1. The derivative of y is going to be a dy dx. So let's start our product rule. The first thing, x, times the derivative of the second, dy dx, plus the second thing, y, times the derivative of the first 1, and I'm not even going to write it in there. Okay. Now let's see. We've got two dy dx's. To get these separate, let me show you all the algebra that's in the book. So here we start. So here's where I left off, right here with the book. Now what we're going to do is plug in the point right away, and we're going to find our slope. But if they asked us to get dy dx by itself, here's all the work you'd have to go through. So first they distribute this 100 to these terms over here, and they distribute, well, let's see. Shoot, we would have to distribute we got to get at least, we've got to distribute this 2 times 3 is 6. We've got to distribute that to this second set of parentheses to get that dy dx out. Yeah, they left the x squared plus y squared as a quantity, so they got the 6 and distributed it to those terms, and then moved the 100x dy dx over to the left side. Let's see, then they factored out the dy dx, got dy dx by itself, so it looks like this, and then they did some simplification and reduced it down to this beautiful mess right here. That's a lot of work. That is a lot of chances to make simple algebraic mistakes. We would go through those steps if they told us to find dy dx, but they did say find the slope at this point 3, 1. So we're going to go through, replace all the x's with 3's, x equals 3, and all the y's with 1's, and see what happens. So we've got a 6. Our x squared, that's going to be a 3 squared or a 9, plus y squared is 1 squared, so that's just a 1. And then our next set of parentheses here, we've got a 2x, 2 times 3 is 6, plus we have a 2 times y, 2 times 1 is 2, and that gets multiplied by dy dx. And then on the other side of equals, we have a 100, and then our bracket. X is a 1 times dy dx, means we have a dy dx here. And then we have plus y, our y value is 1. Okay, very fewer chances of making mistakes now that we're going to be doing more arithmetic than algebra. So let's see what we can combine here. 9 plus 1 is 10. 10 times this 6 is 60 that we are going to distribute here in just a minute. And on the other side, we can distribute the 100 dy dx plus 100. Okay, back to the left side. Let's distribute the 60. So that's going to be 360 plus 120 dy dx equals 100 dy dx plus 100. We're getting close. Okay, let's get our dy dx's on the left side. So here's a 120, and on the other side is 100, so we're going to bring it over and subtract. 120 minus 100, we now have 20 dy dx's. And that's equal to, over on this side we had 100, and then we're going to bring this over and subtract. So that'll be 100 minus 360, negative 260. Ooh, hold on. Did I mess up something? Okay, I found my mistake. If we back up to here when we were first plugging in the 0.3 comma 1, you were probably screaming at your computer, I never put in a 3 for that x. So that should have been a 3 dy dx plus y is 1. And there we go. Hopefully that is going to fix it up here. Okay. Back to the arithmetic. 9 plus 1 is still 10. I got that right. 10 times this 6 is a 60. So we're going to distribute the 60. So this side hasn't been messed up. So that's going to be a 360 plus 120 dy dx. My mistake occurred over here. When we distribute the 100, that's going to be a 300 dy dx plus 100. Okay. Now, I still want to keep my dy dx's on the left, so here we have 120. We're going to minus 300. Yeah, let's keep it on this side. 120 minus 300, that's a negative 180 dy dx is equal to. On the right, we had 100. We're going to subtract 360, so that is a negative 260. Okay, final step, get that dy dx alone. So we are going to divide both sides by negative 180. dy dx equals negative 260 over negative 180. So obviously the negatives will cancel. We can drop a 0. And then the first thing I notice, they're both even numbers, so let's cut them in half. 13 over 9, and it cannot reduce any farther. So there's our slope occurring at that point. And let's see, in this case, they did give us the graph. And if we look at the point in question, it looks like a figure 8 here going through the first and third quadrants at 0.31. We do have a pretty steep positive slope there. So our 13/9 does make sense. Okay. Up next, oh yeah, I guess here's where I show all the algebra that goes into getting dy dx by itself. Again, so if you want to pause the video and go through that, by all means, go right ahead. It is quite a chore. Okay, now this is a little bit different. Example 6, find dy dx implicitly for this equation. The sine of y is equal to x. Then find the largest interval in the form of some negative number with y in the middle and some positive number on which our y would be a differentiable function of x. So first let's derive this. So we're going to derive dy dx. So we're going to derive sine into cos. Oops. Sine derives to cos. We're going to be taking the cos of that same angle y, but since a variable mismatches there, we create a dy dx. And that is equal to the derivative of x with respect to x is 1. So our derivative dy dx is equal to 1 over the cosine of y. Now for the next part, they want us to find the interval on which this would be a differentiable function. Think that it doesn't pass or fail the vertical line test. It says see figure 227. So here's the figure. Our sine of y equals x is a sine wave going along the y-axis. And if we notice, we don't want to fail the vertical line test, so we want to chop off the graph. So we would only have every value between 1 and negative 1 in there, and we would not fail the vertical line test. And from the way the graph is around the origin, that's going to go from positive to negative half pi. If we go outside that interval, we will fail the vertical line test. So our interval is from negative pi over 2 to positive pi over 2, on which our original function would in fact be differentiable. Now it says find out which y is a differentiable function of x. Let's get, what we've got here is the cos of y, and we want x's over here. So let me get rid of, I don't know if I want to get rid of any of this. I'm just going to start a new slide so I can pop back if I need to. So let's see. We need to define the cos of y in terms of x. And how the heck are we going to do that? Well, let's go back to pre-calc. Remember this old faithful, sine squared y plus cos squared y is going to equal 1. Sine squared plus cos squared equals 1. Well, let's get this cos of y by itself. So the cos squared of y is going to be 1 minus the sine squared of y. And then when we take the root of that, we're going to get the cos of y equals the radical 1 minus sine squared. Okay, let me get this out of the way. Now, a lot of these implicit problems, we're going to be going back to our original problem and substituting some stuff in. If I flip back a slide, we've got something about, let me put the sine of y in parenthesis, I can move the squared out here. The sine of y, what is the sine of y equal to? Well, the sine of y can be replaced with an x. So we're going to replace this sine of y in here with an x. So that becomes 1 minus x, and remember it was squared, so that's 1 minus x squared. So the cos of y in terms of x is equal to this, radical 1 minus x squared. So if we go back to here, the derivative with respect to x is 1 over cos of y. Well, we can replace that cos of y with radical 1 minus x squared. Radical 1 minus x squared. There's our derivative with respect to x as a differentiable function of x. Everything is in terms of x. Okay, that was fun. Oops. Example 7, finding the second derivative implicitly. With implicit differentiation, the form of the derivative can often be simplified, as we saw in the last example, by the appropriate use of the original equation. A similar technique can be used to find and simplify higher order derivatives that we find implicitly. So here it says, given this is just a circle, x squared plus y squared equals 25. They want us to find the second derivative, d squared y over dx squared. Okay, so we're going to derive it once, and then we're going to just derive it again. So let's derive with respect to x. The first term is just going to be a 2x, no problem. Our next term is going to be a 2y, but since we are deriving with respect to x, we get a dy dx appears, and that's equal to the derivative of 25 is nothing. So right now, we can divide by 2 and get rid of those 2's. 0 divided by 2 is still 0. And then we're going to subtract x. So we're going to have y dy dx is equal to negative x. And then when we divide both sides by x, dy dx equals negative x over y. Okay, so let me clear this out. So we've got our original function, and now we've got our first derivative. We do want the second derivative, so we're going to derive this again. And what I like to do, I'm going to keep the negative out here. We're going to derive with the quotient rule inside, and then we can distribute that negative at some later point. Okay, so let's get ready to derive with the quotient rule. Our d high is a 1. Our d low is a 1 dy dx. So second derivative, d squared y over dx squared, is equal to, I've got my negative and a big old set of brackets. Now in the brackets, we're going to quotient rule. Low times d high would be a 1, minus high x d low dy dx, all over denominator squared, y squared. Okay, so we're down to this. Now notice we have this dy dx appeared, and we know what dy dx is. dy dx, we can replace that with a negative x over y. So we're going to take out this dy dx, replace it with a negative x over y, and what I'm going to do is just erase this here and put my negative x over y there. Negative x over y. So we have plugged the first derivative into the second derivative, and that will help us simplify it a little bit more. I'm going to do this. Where's copy? Oops, get out of there. Aha. Copy, paste. So I can work on it here without erasing my original work. So let's see, we've got a bracket, still got the negative outside, and then we've got y. This negative and this negative are going to multiply to a positive, and then our numerator times numerator is going to be an x squared, and that's going to be over denominator y. And then down here, we've got our overall denominator is y squared. Okay, so our second derivative is getting there, but it's still, it has some work to do. Usually we don't leave fractions within fractions. And notice our numerator here, we do have a denominator. So if we distribute a y through the numerator, we can get rid of that. So y times y here is going to be a y squared. Plus, when we distribute here, we'll have a y in the numerator that cancels, so that just becomes an x squared. And that's all over. Remember, we've got to multiply our denominator by a y to be fair. So that's going to be y to the third in the denominator. There we go. And I'm going to still put the brackets around it for the negative out front. So there's our second derivative, and that's pretty nice looking. If you left it like that, I would be happy with it. And at this point, we could plug in our point to find our slope. I thought they were asking for a derivative at a point here. No, I've got one in my notes, but I don't see where that happened in the book. All right. Again, this is a good derivative, but notice that numerator, x squared plus y squared. Well, x squared plus y squared is equal to 25. So I can take out, and again, if you left it like this, I'd be perfectly fine with it. But we can take out that numerator, x squared plus y squared, and just replace that with a 25. And then instead of distributing the negative, we can now just attach the negative to the 25. And that's over y to the third. So this is our second derivative, d squared y over dx squared. And again, for some reason, in my notes, maybe it was in an older edition of the book, they wanted the slope at negative 3 comma 4. Negative 3 comma 4. Again, if you left this 25 out and left the x squared plus y squared in it, you'd still get the same answer, because x squared plus y squared would be 9 plus 16, which is also 25. So to actually evaluate this, we can leave the numerator alone as a negative 25 and just plug that 4 in for y. 4 to the third is 64. Our slope would be negative 25 64ths. All right. Up next, example 8. Now they're asking us to find a tangent line to the graph of this, x squared times quantity x squared plus y squared equals y squared at this point, root 2 over 2, comma root 2 over 2. We do have a picture to go with it. Kind of like a parabola opening up, parabola opening down, and we've got this point. So judging by the graph, our slope should be positive. It's going to be pretty steep when we find that slope. Okay. Oh, this looks like it's going to be fun. We've got x squared, and then a quantity x squared plus y squared equal to y squared. Now this is also one that says find the tan line, so we just need a slope. We might find dy dx. Oh yeah, looking at my notes, we are going to take this all the way to dy dx because it's just good practice, and it does simplify down nice before we actually plug the point in. Let's see. And the way I did this in my notes, we could do product rule here with that as our first and that as our second. But an alternate method, I distributed this x squared to get the party started. So that gave me an x to the fourth. We can derive that just fine. And then we're going to have a plus x squared y squared. We're going to derive that with the product rule. So I guess there is no escaping the product rule on this one. Okay, let's start deriving. Remember, we are deriving with respect to x. So I'm going to come down here. First term is nice, easy. X to the fourth, that's going to become a 4x cubed. Plus, here we're going to do a product rule where the derivative of the first thing is going to be a 2x. The derivative of the second thing is a 2y, dy dx, created by the chain rule. So I could put brackets here, but since we're adding, there's no negative to distribute. We can dispense with the brackets. And then our product rule is going to be the first thing times the derivative of the second plus the second thing times the derivative of the first. And that's going to equal, on the other side there, we derive that to get a 2y. And again, a variable mismatch. So over here, we also have a dy dx. So let me move this up here. Oops. And I'm going to underline any term that has a dy dx component. So this one does. We'll keep that on the left side here. Over here on the right, this is also a dy dx. So we're going to bring that one over by subtracting it. So let's start here. I'm going to move this 2 to the front. So I'm going to write 2x squared y dy dx. And then this term again is brought over by subtraction, minus 2y dy dx. And then we have our equal sign. Well, on the other side of equals, there's a 0 over there now, but we're going to move over this term by subtraction, minus 4x cubed. That's a terrible cube. That's just as bad. There we go, that's a little better. And then this term will also be subtracted, so on the other side it's a negative 2x y squared. Okay, so we've separated the dy dx terms and the non-dy dx terms. Over here on the left, we're going to bracket that off and factor it out. So we have dy dx times quantity, 2x squared y minus 2y, close bracket. And that's equal to negative 4x cubed minus 2x y squared. And last term is to get, or last step is to get dy dx alone. So we're going to divide by the quantity in the brackets. Dy dx, our derivative is on the left or on the numerator, negative 4x cubed minus 2xy squared, all divided by 2x squared y minus 2y. Now we could just plug our point right into there, but a very helpful part of this is going to be to pull out whatever we can in the numerators and the denominators. So let's see here. Numerator, let's factor out a 2, and we can pull out an x, pull out a 2 and an x. So let's see, that'll leave us a negative 2x to the second minus 2y squared. Or no, minus y squared. We factored the 2 out. Minus y squared. In the denominator, we can also factor out a 2 and a y. So after the 2 and the y come out, that's going to leave an x squared and a minus 1. And we'll close off that. Now we're getting ready to plug the point in, but let's make a little note here. Our point is root 2 over 2, comma, root 2 over 2. So we're going to replace the x's and the y's with the exact same thing. And let's see what happens when we square either of these. Since they're both the same, if we take it and we square it, we're going to get a 2 over 4, or 1/2. So x squared and y squared are both interchangeable with a half, and x's and y's are both interchangeable with a root 2 over 2. So when we actually start plugging in here, this is going to actually simplify down nice. First, we can drop the 2's. They're equivalent, divide them out to a 1. Out front here, let me do my big divider line. This x is going to be a root 2 over 2. This y is going to be a root 2 over 2. So in a little later, we're going to cancel those. Oops. Okay, now we're inside the brackets. In the numerator here, we've got a negative 2, and then this x squared is going to turn into a half. And then we've got minus, this y squared is going to be the same thing, 1/2, close brackets. Denominator, this x squared is also going to turn into a 1/2 minus a 1. So let's see what we're left with here. Minus 2 times 1/2, that's a negative 1, minus a half more. Denominator, 1/2 minus 1 is negative a half. So the numerator, negative 1 minus a half more, is negative 3/2, and that's divided by a negative 1/2. We can cancel the negatives and then invert and multiply. 3 over 2 times 2 over 1 is 3. There's our final slope. Now remember, they did ask us to find the tangent line. So we found our slope, 3, and we've got a point. Our slope is 3. Our point is root 2 over 2, root 2 over 2. So let's find that tan line. Y minus y sub 1 equals m times quantity x minus x sub 1. Let's see here. We're going to distribute the 3. Y minus root 2 over 2 equals 3x minus 3 root 2 over 2. And to get y by itself, y equals, we've got a 3x, and then we're going to have a negative 3 root 2 plus negative 3 root 2 over 2 plus a 1 root 2 over 2. So we can combine those terms. We have, yeah, don't get the root 2 is sort of like a variable. So we've got 3 of those root 2's plus another one of those root 2's. So we've got 4 of those root 2's. Back. I forgot that was a minus 3 and a plus 1. Minus 3 plus 1 is a minus 2 root of 2 over 2. And then those 2's are going to cancel. So our final tan line is y equals 3x minus the root of 2. Okay. Now we get to some of the trickier ones. This technique, logarithmic differentiation. And it says here, it's convenient to use logarithms as aids to differentiating non-log functions. This procedure is called logarithmic differentiation. So here's our function. Y equals x minus 2 quantity squared upstairs, radical x squared minus 1 downstairs. If we were to derive it in this form, we would need a quotient rule. And then our d high would require a chain. Our d low would require a chain. This could quickly turn into quite a mess. So the way we're going to approach this, remember we can do this something to one side. If we do it to both sides, we have to be fair. So our first step here is we're going to natural log both sides. We've got the natural log of y is going to equal the natural log of this mess. X minus 2 quantity squared over root x squared plus 1. And the reason we do this is now we can use the properties of logs to simplify this, like we saw in when we did the section on the chain rule and we started looking at logarithmic differentiation. We saw this. Now I'm going to run out of room very quickly, so I'm going to sort of disregard this ln of y for a little while. It is very easy to forget that we did this step, and at the very end you're going to get an answer. And remember, the answer you find is not y equals, it's the natural log of y equals. So at the very end, we're going to have to get rid of that natural log that we introduced in this first step. Okay, so let's start busting this up. The first thing I like to do is separate the numerator and denominator. So we are going to have the natural log of the numerator x minus 2 quantity squared minus the natural log of the denominator, and I'm going to put it as a 1/2 power. X squared plus 1 to the half. Notice this isn't a negative a half. We did not bring it up, so to speak. We are using the properties of logs. So that is to the positive half power. Next step, we're going to bring those exponents down. That's going to make life much easier. So this becomes 2 natural logs of quantity x minus 2 minus 1/2 the natural log of quantity x squared plus 1. Okay, we're getting somewhere. Get this out of the way. It looks like we are ready to derive. Let me move this up here. So the 2 is a constant multiple. That's going to come along for the ride. When we derive natural log of a quantity, that quantity becomes our denominator. And the derivative of that quantity goes right on top. Derivative of x minus 2 is a 1. And then we've got minus 1/2 is a constant multiple. And then we're going to derive this natural log quantity. That quantity that we are logging is our denominator. Derivative of that would be a 2x, goes right up on top. Okay, and I see we can cancel these 2's on the diagonal. Ooh, and I should have pointed out on this, I guess I did have room for my ln of y there. So this was equal to the ln of y, and we derived this side, so let's derive the natural log of y. When we derive that, what we are logging, y becomes our denominator, and the derivative of that, y prime, or dy dx, is going to go right on top. Okay, so here we are. Oops. Next step, let's get this to be one big fraction. Let's do a little more work here. I'm going to change that dy dx to a y prime just to make it a little easier to write. So let's see here, we're going to have a 2 on top over a quantity x minus 2. And after these 2's cancel, we have minus 1 over x squared plus 1. Okay, we are going to combine those into one beautiful fraction, and it doesn't look like it's going to be too bad. So when we combine these, our common denominator will be these 2 multiplied together. I do not recommend foiling that out. And we're going to multiply this 2 by this denominator, 2 times quantity x squared plus 1. And then we have a minus 1 times the other denominator, x minus 2. And again, this is equal to y prime over y. Next step, distribute the 2 and the negative 1, and we can combine like terms. So this is still y prime over y. So let's see here, we'll distribute there and get a 2x squared. If we distribute here, we'll have a minus x, and then we'll have a plus 2 and a plus 2 more. Oops. And I think I messed up again. Let me back up. When I was combining those fractions, I think I lost part of a numerator. Yes, when we canceled the 2's on the diagonal, I still should have an x in my numerator. Up here, I'm messing up so bad. Yes, I dropped this x. That x, you again probably screaming at your computer. What are you doing, Keyser? There should be an x right there. So that's x squared plus 1. I apologize for the mistake. We all make mistakes. Back up here. Okay, now let's get this to be one fraction. Y prime over y equals, let's see, common denominator, x minus 2 over x squared plus 1. This 2, let's distribute it right now. So we're going to distribute that 2 across this. So that's going to be a 2x squared plus 2. And then here is a negative x that we're going to distribute across the other denominator. So that's going to be a negative x squared minus 2x. or excuse me, plus 2x. Yeah, because we distribute that negative to this negative, that becomes a plus. Okay. Let us combine like terms in that numerator. We've got a 2x squared minus another x squared. That leaves us 1x squared. We've got a 2x and a 2 plus 2x plus 2 all over our denominator, x minus 2 over x squared plus 1. Okay, we're almost done. Remember, we wanted to find the derivative y prime, or dy dx. We are almost done because to get this y prime by itself, we're going to multiply both sides by y. So this y is going to hop over here. And at this point, we can go back to our original equation. I think I dragged it up to somewhere I cannot. Oh, nope, there it is. So here is our original y equals. We can take this y equals and plug it in for this y. So I'm going to do that in a different color. We've got dy dx, our derivative that we're looking for, our final answer. We're going to replace this y with the original function, x minus 2 quantity squared over radical x squared plus 1. And then we're going to multiply that by the stuff we found above, which I'll go back to blue to write down. So we're going to multiply the numerator by x squared plus 2x plus 2, denominator by the term x minus 2, and x squared plus 1. And there it is. Our final derivative, dy dx, equals that algebraic mess. It is correct. It might not be very pretty. It's kind of complicated, but it is very correct. It says here you could also solve the problem in example 5 without using logarithmic by using the power and quotient rules. It says use these rules to find the derivative and show that they are equivalent. Which method would you prefer? Probably going to prefer logarithmic because that is going to turn into quite a mess. Okay. Next up, example 10. Ooh, this is the last example for this section. Hallelujah. We've got this. Find the derivative of x to the 2x power for all x's greater than 0. Okay, this looks like it's going to be tricky. Y equals x to the 2x. You know, we've got a variable in our exponent also, and it'd be easier if we could bring that down, and we're going to do the same technique we saw in the last one. We're going to take the natural log of both sides. When we do that, this 2x exponent is going to come down front. So now, go back to black ink, we've got the natural log of y is equal to 2x times the natural log of x. Okay, so the exponents come down, and that's usually a source of some grief. So now let's derive both sides. The derivative of this side is going to be dy dx, or y prime, over y. Remember, when you're logging something, what you are logging is your denominator. Derivative goes right on top. When it comes to this other term, we're going to need the product rule. We've got two things. Let's see, the derivative of the first thing is 2. The derivative of the second thing, ln of x, derives to 1 over x. So when we derive this, we're going to have the first thing, 2x, times the derivative of the second, plus the second thing, ln of x, times the derivative of the first, and I'm going to put my 2 in front of that ln so it doesn't look like the ln of x2 or 2x, so it looks a little better like that. Okay, let's see if we can simplify a little bit, maybe use some algebra. Well, let's see here. In this term, 2x times 1 over x means we can put the 2x on top. So the x's are going to cancel. So we can write y prime over y equals 2 plus 2 natural logs of x. All right, to get our derivative alone, we are going to multiply both sides by y. So again, to get dy dx by itself, I'm going to bring this y over. We're going to multiply, but of course we would need a set of grouping symbols there. So y times the quantity. So our derivative, y prime, equals, well, we've got the y here. Let's replace it with our original x to the 2x power. And then we've got a 2 plus 2 ln x. 2 plus 2 ln x. And if you left your derivative like that, I would be very happy. If you're on an AP test, maybe it doesn't match some of the multiple choice question or multiple choice answers. Something else you could do is factor out this 2. So that 2 could come out here in front. You might see an answer like 2 or 2x to the 2x power times quantity 1 plus natural log of x. Might look a little better. Okay, let's see what it says down here. I think we're done. Here are some guidelines for logarithmic differentiation. In general, use log differentiation when deriving 1. A function involving many factors, or 2. Functions having both a variable and a base as a variable exponent. Okay. Do I have, here's the homework assignment out of the book, page 179, these problems, and there are 5 questions on WebAssign. I will see you in class.